All right, next up, Keith Sherburn will talk about his presentation. It's horizontal shearing instability and its potential role in QLCS Mesovortexgenesis. Go ahead, Keith.
Yeah, thanks, Mike. And yeah, now for something entirely different here. But great representation from the South Dakota offices today. I get all three represented by speakers here. So good morning. Thank you for taking the time to attend. I'm going to start off here by just noting a couple things before we dive into the slides. And I'll start by saying early on, this talk is going to briefly dive into some of the math associated with horizontal shearing instability. Don't worry, we're going to move on from that pretty quickly, but just wanted to give you a fair warning. And also before we get started, I want to note that this isn't meant to be an intimidating presentation. You know, we're going to be discussing a mechanism that's likely responsible for mesovortexgenesis in many QLCSs that really isn't all that well understood or anticipated just yet. And I certainly don't have all the answers when it comes to this mechanism or its operational implications either. But I'm hopeful that this presentation and some additional QIP training materials will set you up for success if you see this manifest in a real event. So with that in mind, let's dive in. So I'll start with some motivation for this topic. For those who don't know, I'm a member of the Central Region Convective Warning Improvement Project team, or QIP, as I mentioned before. And we've recently released some modules referencing horizontal shearing instability. But in some of our internal discussions, we agreed that some additional context on the concept of horizontal shearing instability, or HSI, might be helpful for a more thorough understanding of these modules. So to begin, we're just going to start with a simple question of what is horizontal shearing instability, or HSI? And HSI is, in its most basic sense, a means by which vortices can arise from initially straight flow. So in today's context, we're going to view this in largely XY space, so horizontal space. But horizontal shearing instability is essentially the same mechanism by which Kelvin-Helmholtz waves can form in the vertical as well. In these circumstances, whether horizontal or vertical, an initial corridor of large vorticity, aka a vortex sheet, evolves into somewhat regularly spaced and either circular or elliptical vortices following some initial perturbation. There are a couple different criteria required for the potential development of HSI, the Rayleigh and Fjortov criteria. The formulas for the criteria are listed here for those so inclined to step through the math. Here, U bar is the mean wind speed parallel to an initial shear axis, and Y is the direction normal or perpendicular to that shear axis. And rather than focus on the math, I just want to impart the physical explanation of these two criteria. First, the Rayleigh criterion states that there must be an inflection point somewhere within the mean flow, whereas the Fjortov criterion essentially requires that vorticity must be maximized at that inflection point. So what does this look like in practice? Well, if you use the Markowski and Richardson text from 2010 at some point, either in a classroom setting or in a training setting, you may remember this figure, which shows 5 different mean horizontal wind profiles. So these are highly idealized, just showing how the mean zonal wind, in this case, changes in the north-south direction. And the task here is to assess, based on these profiles, which would be potentially associated with HSI. So let's recall the two criteria. First, you need an inflection point in the horizontal wind profile, which just basically means you have a change in curvature in the profile. And that knocks out the top left and top middle profiles, which do not include an inflection point. They just have constant curvature in the Y direction. The other 3 do include an inflection point, which is marked by the blue dots with the uppercase I label that you see there. But let's consider the second criterion as well, that the inflection point must be co-located with a local maximum in vorticity. This is not true for the profile here at top right, which has its maximum vorticity closer to Y equals 0 on the plot. So we'll knock that one out as well. But both of the profiles at the bottom do have an inflection point that's co-located with a vorticity maximum, meaning that they could be associated with HSI. Basically, that means that they could be unstable to small perturbations. But don't forget that these criteria are necessary but insufficient for the release of HSI. So just because you meet the criteria does not necessarily mean that you will get horizontal shearing instability or the release thereof. So just based on this initial look at some profiles that might be conducive for the release of HSI, you can get the sense that these criteria are commonly met along interfaces that separate different air masses, like outflow boundaries, cold fronts, etc. So as such, there have been several past studies that have identified HSI release as the mechanism responsible for the development of vortices, and this is at a variety of scales. So here, observations along air mass boundaries from the International H2O project, which is called IHOP, if you like pancakes, back in 2002, that shows the development of mesovortices along air mass and outflow boundaries that they attributed to HSI release. And if you're unfamiliar with the terminology of mesovortices, they're just vortices at a smaller scale than mesovortices. Earlier simulations of convection along outflow boundaries also show that deeper and stronger vortices can readily form as a result of HSI release. So in their series of papers from 1997, Lee and Wilhelmsen documented the developments and evolution of both mesovortices and several non-supercell or non-mesocyclonic tornadoes along pre-existing outflow boundaries. At left here, which was from their first paper in this series, this figure depicts the development of mesocyclonic vortices through time. Of note, you'll see that these are not symmetric, so some vortices develop more quickly than others, and that's owing to the uneven distributions and amplitudes of the initial waves, or what they called clefts, within the outflow. And with time, the stronger vortices eventually become occluded and dissipate, similar to what you would expect in tornadogenesis. However, the authors also noted that new vortices might subsequently develop along those remnant waves, and you can actually see some of that occurring here as you step through time from left to right. Lee and Wilhelmsen also highlighted similarities between these simulations' prior observational work associated with mesovortices along thunderstorm outflow boundaries. So in this case, this was just a general air mass boundary, but they noted there were similarities to previous studies looking at outflow boundaries. Then at right, we see a 3D rendering of similar vortices that are in the process of evolving into non-mesocyclonic tornadoes. You notice with time, which goes from top left to top right down to the bottom panels here, you get consolidation of vortices. So you go from 7 down to 4 different vortices. And this coalescence is actually caused by a subharmonic interaction. So there's 3 different stages of evolution within the HSI release process. You have exponential growth predicted by linear theory, nonlinear growth, and then subharmonic interaction. So we're not going to go into all that, but in short, you can tell this can be a fairly complex process. So just based on these couple of examples, and no doubt from anecdotal evidence from those with several years of operational experience, it becomes clear that HSI might be responsible for vortex development at a variety of scales along air mass and outflow boundaries. Some prior work, especially from authors like Matthew Clark at the UK Met Office, showed that mesovortex development along narrow cold frontal rain bands, or NCFRs, may also be largely associated with, or at least aided by, the release of HSI. And consistent with the theme of this presentation here, HSI release might be responsible for mesovortices along the leading edges of QLCSs and bow echoes in some circumstances. So to illustrate this potential, let's consider a north-south oriented QLCS here with outflow boundary shown there with the frontal ID there. You have strong pre-line southerly flow. You have pretty strong post-line northerly flow. And admittedly, this is a largely idealized scenario, right? It's likely not going to be replicated perfectly in reality. But you could conceivably observe a wind profile that's awfully similar to one of the examples we just saw from Markowski and Richardson, which we established before does meet the criteria for HSI release. So it stands to reason, based on theory, that we could get HSI release along leading edge of QLCSs. And it's worth noting here that this appears to be true regardless of the vertical wind shear magnitude in low levels. And this factor, or this mechanism, may actually be more closely tied to line parallel shear versus line normal shear, and the latter of which is emphasized in the 3 ingredients method. So let's dive more into HSI associated with QLCSs specifically. So in their relatively recent 2019 paper, Conrad and Knupp conducted a case study of a tornadic QLCS that occurred across the Tennessee Valley during January of 2015. Therein, shown at left here, they actually went and calculated the Rayleigh and Fjordhoff stability criteria across the QLCS, demonstrating that both criteria were indeed met in the vicinity of the associated outflow boundaries wind shift. They went ahead and estimated the width of the shear zone along the outflow boundary, found that to be about 2 to 3 kilometers, and they confirmed that spacing of vortices along the line was consistent with the range of anticipated wavelength, owing to the release of HSI, which previous modeling studies showed was about 7.9 times the width of the shear zone. And you can see it right, both in reflectivity imagery and velocity on the bottom. There are a couple distinct mesovortices at this time. Ground relative winds here are also shown at the bottom right. And you might remember, in those idealized wind profiles we were looking at before from Markowski and Richardson, there was a 180-degree wind direction change along the outflow boundary. It went from due southerly to due northerly. Here, the angle is much lower. It's closer to probably about 60, maybe 70 degrees if you're looking at farther into the outflow and farther into the inflow there, or preceding the line. This is consistent with Clark and Parker back in 2014, who showed that angles around 60 degrees were sufficient for HSI release in their tornadic narrow cold frontal rain bands. There was the caveat there that the post-frontal winds, so the winds in the wake of the cold front, were at least as strong as the prefrontal winds. And we'll show that in a little bit more detail here near the end of the presentation. Now, the next several slides are going to focus on the results of a recent study by Goodnight et al., which attempted to determine the number of tornadoes within QLCSs that were associated with 2 different formation mechanisms. So the first, which is what they termed to be the pre-tornadic mesocyclone dominant process, is, as noted, dominated by the development of vorticity via primarily baroclinic processes. And this is similar to the mechanism that produces cellular tornadoes just within a QLCS. And the second is dominated by the apparent release of HSI. So this is really more focused on what we're discussing today. In the figures on the subsequent slides, which I have several figures from this particular paper, they're referred to with the acronyms of PMD and SID, respectively. So similar to Conrad and Knupp, Goodnight et al. Did attempt to estimate the shear zone width in order to provide further support for the release of HSI. This was assuming that radar data was sufficient to do so. And as noted before, there was that modeling study back in 2016 that showed the most unstable wavelength was about 7.9 times the width of the shear zone, give or take a kilometer or so. And you can see this example from Goodnight et al. Did have vortices spaced out at around 7 to 7.5 times that shear zone width. So pretty consistent with what you would expect from HSI release. So diving into some of their results, Goodnight et al. Showed that QLCS tornadoes in this shearing instability dominant cases, so based on the release of HSI, tended to be slightly more common from January to March or from late winter to early spring. But overall, they're pretty similar annual climatologies, especially given that HSI was colloquially thought to be more of a cold season or cool season phenomenon. So that was an interesting finding right off the bat. The icons at left here might be a little tough to see depending on the size of your screen, but the ultimate takeaway from this map is that most of the country, especially as you get east of the Rockies, can experience QLCS tornadoes via either of these mechanisms. At right, the diurnal cycle reveals that the shearing instability dominant process accounts for a large fraction of cases during the overnight and morning hours, especially here as you get to say around 9 to 12 local time or 9 p.m. to midnight local time as well. But the pre-tornadic mesocyclone dominant mechanism is dominant during the local afternoon and evening hours. So you can see the orange bars really comparatively are a lot larger here as you get to 3 to about 9 p.m. local time. So the authors only briefly elaborated on this feature of the climatology, but they noted that it implies there's a strong link between that PMD process and diurnal heating. It makes sense if the primary source of vorticity is baroclinic like it seems to be in a lot of supercell cases as well. In the data sets as well, they found that tornadoes associated with HSI were skewed slightly toward lower EF skill ratings compared to PMD cases, but percentages were overall pretty similar, within about 5% of one another. As you would expect, the distributions of low-level delta V are also skewed towards lower values within the HSI sample, which is consistent with those lower EF skill ratings. I'll also note that they're providing delta V here in meters per second. So about half of what you would expect for delta V in knots, or close to what you would expect in terms of VROT if you're looking at knots. With that said, if you look at the right-hand side of this figure here, you'll see that even in the same rating category, tornadoes associated with HSI tended to have weaker low-level delta V. You also see that although the delta V distributions for HSI cases are about identical for EF0s and EF1s, there is a notable increase when you get up to EF2s. So the 25th percentile delta V here of EF2s is comparable to the 75th percentile in both EF1s and EF0s. So it's important to mention that these values were sampled while the tornadoes were ongoing. So they don't provide us necessarily with any discriminatory information prior to tornadoes, but the differences here nonetheless might help with diagnosing particularly strong tornadoes associated with this SID mechanism. If you get to values of about 35 meters per second or 70 knots in terms of delta V, you could be dealing with a higher end, relatively, tornado. Then at left, we see that in this study, tornadoes associated with HSI tended to be sampled at a lower height than those associated with the pre-tornadic mesocyclone dominant mechanism, meaning that, well, there's a couple things that this means. First, they were more easily observed close to a radar, but it also means that the relative depth of vortices associated with HSI are shallow compared to those associated with that pre-tornadic mesocyclone feature. So as you get farther and farther away from radar, it may be more difficult to actually identify these in real time. So with these results in mind from the Goodnight et al. Study, let's dive into some example cases here. And this first one is one of the more prolific examples of potential HSI release that I personally can recall. This event occurred during the early morning hours of January 30th in 2013. Here you see there's a well-established QLCS. It's crossing Middle Tennessee from west to east via reflectivity and velocity imagery. Here you see several localized surges, inflow notches, some reflectivity nubs, all evident. So these things that we look at in terms of the mesovortex warning system to either increase our confidence, potentially nudge us one way or another in warning operations. But many of these reflectivity features coincide with mesovortices on velocity as well. So the Nashville metro area, that's the Old Hickory radar here, shown by the yellow dot. Nashville metro area is just west there. You see that several of these vortices that are west of the Nashville metro are relatively evenly spaced, as shown here with the annotations. You also have some a little bit farther south that we'll get to shortly. If you jump ahead about 20 minutes, we see those aforementioned features become more numerous at this time. So again, labeling all the vortices here. There also appear to be multiple areas of potential HSI release, potentially different wavelengths here of vortex development. I have tighter packing of vortices to the north compared to increased distance between each vortex as you get farther south along the line. If we step ahead another 10 minutes in time, and I'm not going to label each vortex in this particular radar image, but note the very pronounced areas of roughly equally spaced rotation that are evident still via both reflectivity on the left and velocity on the right. And I should note that this is storm relative velocity in this particular case. At this time, you even start to see some subtle waviness to the shear zone farther north into south central Kentucky. And within the next half hour to hour, several mesovortices and even a few tornadoes develop within that portion of the QLCS as well. And if you go back to the early figures I showed, you may have noticed that that waviness is a precursor to the release of HSI. But given the complexity of the process, the timing from those first perturbations to ultimate mesovortexgenesis and potentially tornado genesis is unclear, as are any potential failure points that might occur along that process. So here the time is about 10 minutes later, and I've actually zoomed in to the portion of the line from around the Nashville metro area northward into south central Kentucky. Here you can really get a sense of how distinct yet fine scale some of these vortices can be. You have 5 vortices that are pretty easily identified within just a county or two in northern Middle Tennessee. And each of these vortices is also associated with some clear clues via reflectivity also. Most notably, you have some reflectivity nubs that are very distinct. Now, I want to step back. This image is actually a few minutes prior to the initial tornado genesis in this case. So this was about 8Z, so what, 2 a.m. local time there in Middle Tennessee. And you'll see a few notably stronger convective cores near the middle of this image, along with some, again, relatively evenly spaced cores as you get farther north. There's also a very distinct shear axis along the outflow boundary here. Very strong inbounds, and this is back to base velocity here, so we're no longer looking at storm relative velocity. But you have very strong inbounds or southerly southwesterly flow ahead of the line, and then relatively weaker inbounds to even near zero flow as you get on the backside of the line here within the QLCS and the outflow. So this line here demarcates a very strong shear axis, which ultimately facilitated the release of HSI. Now, I want to look briefly at the environment just to give you a sense of what types of environments these can form in. They're kind of the bounds of them. This ended up being a rather extreme example of a high shear low cape environment, at least per the SPC mesoanalysis. So we have a single 250 joules per kilogram mixed layer cape contour here, analyzed in Middle Tennessee, which coincides with 70 to 80 knots of effective bulk shear. Might be a little tough to see the vectors there, but that's what they're showing. And then if you look at the 0 to 1 kilometer bulk shear vectors, one, they're largely parallel to the advancing QLCS, but you also have magnitudes here of about 50 to 55 knots in advance of the QLCS. So very impressive kinematic environment. If you turn your attention to some of the environmental parameters referenced in the mesovortex warning system, starting on the left here, the 0 to 3 kilometer cape at the time seems to be pretty meager. Values are under 25 joules per kilogram, according to the SPC mesoanalysis. Now, I'll note this is a high shear low cape environments, which tend to be associated with fairly narrow zones of destabilization right ahead of the storms. So this might be underdone a little bit, given the 40 kilometer grid spacing in the SPC mesoanalysis, but taking it at face value, it seems like that particular nudger would not be met. You do see very strong surface vorticity, though, analyzed along and behind the QLCS. If you turn over to 0 to 3 kilometer shear vector magnitudes, they're very strong, again, in this situation, values around 65 to 75 knots ahead of the QLCS. And although the orientations might be more parallel than normal to the line, these strong magnitudes make it likely that the shear-based ingredient of the 3 ingredients method is going to be met in any subtle region of bowing or surging. So in this particular case, the 3 ingredients method may have actually worked out pretty well. Altogether, this event culminated in the largest January tornado outbreak in Middle Tennessee history. It's actually the second largest tornado outbreak, regardless of month in that area, second only to the super outbreak of April 1974. And although the majority of tornadoes were EF0s or EF1s, you also see that there are a few EF2s embedded therein. And again, you'll see the relatively evenly spaced, as we saw with the vortices, relatively evenly spaced tornadoes as well from north to south, especially along the, or north of the I-40 corridor here, which runs west to east through Middle Tennessee. Now, wrapping up, these next couple of examples are going to be relatively short, but just wanted to reinforce the ideas we've discussed throughout this presentation. This here was an event that occurred just this summer in Chicago's area. So this was not a high shear low cape event. This was higher cape, a little bit weaker shear. And compared to the previous event, this was a much smaller scale convective feature. You might struggle to call this a QLCS or MCS even, but nonetheless, along the leading edge, you see several different reflectivity nubs here, maybe not quite as distinct as what we saw before, but those reflectivity nubs and inflow notches were co-located with mesovortices in velocity imagery. And this event featured both significant straight line winds and a brief EF0 tornado, the path for which is shown here. And finally, one last event that occurred near San Antonio, Texas. This was featured in some of our recent QIP training modules and within the Goodnight et al. Manuscript as well. But here it seemed like both of those dominant mechanisms discussed in the Goodnight et al. Paper might have been present. So you see relatively evenly spaced vortices along the QLCS leading edge here, but you also have this stronger, more mature vortex deeper within the QLCS that appeared to form before these other vortices and formed via the so-called pre-tornadic mesocyclone dominant mechanism. And having gone through this case in one of the QIP training modules in one of our warning example modules, it was clear that the 3 ingredients method worked pretty well for that particular vortex, maybe not quite as well for the others. And the QLCS in this case was responsible for several different tornadoes. 3 of those were EF2s, like in that first example from Middle Tennessee. So to review here, horizontal shearing instability is a mechanism through which a vortex sheet, such as along an outflow boundary, along an air mass boundary, can evolve into a line of relatively evenly spaced and like-signed vortices. In order for this to occur, an inflection point in the mean wind profile must be co-located with a local maximum vorticity. I'll note, as I've mentioned throughout this presentation, the timing of this evolution is not easily predicted. It seems to be a pretty complex evolution going from the initial waviness into the development of vortices due to a combination of linear growth, nonlinear growth, and subharmonic interaction. But in some of these cases, it may be a little bit more clear that you're going to start to see this occur, and you can be a little bit more alert when it comes to warning operations in those cases. Based on recent research, it seems like this mechanism might be responsible for about half of tornadic QLCS mesovortices, and it's especially prominent during the overnight and morning. So this is a very important consideration as you get into operations of severe convection in QLCSs. So through some idealized examples, we saw wind direction changes of 180 degrees along the shear axis early in the talk, but Clark and Parker, that paper back in 2014, showed that veering of 60 degrees or so was sufficient for tornadic mesovortices to form, as long as the wind magnitudes behind the associated front or outflow were at least as strong as the prefrontal flow. And that's shown here in this figure. So I'm going to step through this here briefly. We're split into 3 different categories here. In the red, we have the cases with strong postfrontal winds and large wind veer. It's a large change in the wind direction as you go across that outflow boundary. These cases were all tornadic. In yellow down here, there's only a couple of cases, but these were characterized by strong postfrontal winds and small wind veers, so not much change in the wind direction as you go along that outflow boundary. These were actually non-tornadic. And then in the green at left, these cases all had weak postfrontal winds, and these 2 were non-tornadic. So the only ones that were consistently tornadic were those that had both the strong postfrontal winds and the significant change in wind direction as you went across that outflow boundary. Now, admittedly, research on environmental influences on HSI release is somewhat limited thus far. So we don't have a good handle on how the environment might impact the associated vortex strength or the timing of HSI release or even the likelihood of HSI release. But what we do know is that HSI release can occur very quickly. So you get that nearly simultaneous formation of several vortices along the leading edge of a QLCS. So again, I can't state this enough. This has significant implications on warning operations in QLCS events. So I'll put a plug in for our recent QIP module that focuses on QLCS polygonology, which Fred Glass worked on, which provides some examples and suggestions for warning during such events. And speaking of the QIP materials, ultimately it's unclear how well the mesovortex warning system and the 3-ingredient method might anticipate mesovortexgenesis in these cases. And the Goodnight et al. Research actually suggested that the system might not be quite as skillful in these situations compared to when you have the pre-tornadic mesocyclone dominant mechanism. But I'd say the jury is still out to a degree, just because of how early we are in the research associated with this mechanism and the events as a whole. So with that, I think I'll just leave these summary bullet points on the screen and take any questions that you may have. If you have any further questions after the fact, feel free to send me an email, keith.sherburn@noaa.gov, and I'll get back to you as soon as I can. So thanks.
Great job, Keith. We have a question in the chat. Can you see it from Brian?
Let's see. Yep, thank you for presenting. How does the release of HSI act synergistically with vortex stretching via an updraft or vertical tilting? Seems to me that one can't participate in the release. Yeah, it's a very good question. I think if you were going to get HSI being released without an overlying updraft, what you would get is just the very quick demise of all of those vortices, right? You need an overlying updraft to facilitate the stretching and to prevent the downdraft from being dominant locally and just dissipating the vortex. So absolutely, you need, whether it's buoyancy driven or dynamically driven, you need some sort of overlying updraft that can help with stretching the vortex. Tilting is not as much of a consideration here, just because you already have the vertical vorticity in place. It's not just horizontal vorticity that's being tilted and then stretched. So you almost skip the tilting aspect here. It's really just the stretching. Now, it could be that you get that stretching both at the bottom and at the top. I mean, you could get a rear inflow jet reaching the surface, increasing your convergence, which aids in that stretching. In addition to the updraft that overlies those vortices. But yeah, you really do need the updraft in place, I think, for this to succeed. I hope that made sense. Sorry, I was just kind of working through it on the fly there, and I'm introverted, so I don't, I'm not as eloquent with my words as some folks may be when they're thinking things out.
Yeah, it looks like you answered the question. So any other questions? Last call for questions for Keith.
Yeah, I see John's note there about looking at the May 12th, 2023 case. Be happy to do so. Longer term, because this is something that I think deserves a lot more attention in the operational space and probably in the research space as well. But I would like to start developing a case list for these so we can start to get a better idea of, how quickly do you go from those initial perturbations along the line that you can identify somewhat via velocity imagery, assuming that you're close enough to radar. How long does it take to get from those to the mesovortex to the tornado? How does that vary depending on the environment and so forth? Because yeah, I see this being a significant issue since the Goodnight et al. Paper showed that it accounts for half of the tornadic mesovortices. It's certainly something that deserves a bit more attention.
Looks like we have another question from St. Louis in the chat.
Yeah, and they asked how can you differentiate between when HSI is being released versus the PMD type scenarios. That's a good question as well. I mean, the last example that I showed here from San Antonio indicates that they can coexist. So it's not necessarily going to be one or the other in any particular case. PMD type scenarios tended to be associated with deeper vortices prior to the development of strong surface vertical vorticity. Said another way, it's similar to in a supercell where you have kind of some mid-level area of rotation, then you start to develop low-level rotation that eventually leads to a tornado. The PMD cases tended to be deeper, according to the Goodnight et al. Data set. But ultimately, I think they can coexist. The one thing to keep an eye on, if you see that you have a very distinct shear axis, very strong shear axis, where you have strong veering flow as you go along the outflow boundary, and you start to see some waviness in what was previously just very straight flow along the leading edge of the line, I would start to be concerned about the potential for HSI release in that case. And these can be, as I noted throughout the presentation, these can be tough to anticipate, and they can be especially tough to warn on if you're being reactive, because in these cases you have several vortices that all develop relatively simultaneously along a segment of the line. It could be a long segment of the line or relatively short. But I've faced this dilemma in operations myself. Do you try to sharpshoot based on seeing these start to develop, or do you just issue one larger warning? So I'd be focused more on, I'd say, the operational implications versus just what the formation mechanism is. And regardless, if you see these types of this waviness or these vortices starting to develop, have an idea of what you're going to do if they start to or continue to evolve in the way that they potentially could, which could be you have 3 or 4 mesovortices that all produce tornadoes around the same time, like we saw in the Nashville case. So I'd again point you to Fred's polygonology module for some additional insight on that. But I'd be happy to chat with you after the fact too. And like Mike also asked, do you envision any changes forthcoming to the mesovortex warning system or the 3 ingredients method based on HSI? Any sort of training methodology has to be reviewed at recurring intervals as you start to get additional research findings and results that come in. Given that there's a fairly high profile field project that's focused on QLCSs right now and QLCS Mesovortexgenesis, tornado genesis with the Perils field project, there are a lot of studies that are looking at things like this, looking at what is the required shear magnitude. We have 30 knots there in the 3 ingredients method for the 0 to 3 kilometer shear magnitude that's normal to the line. Should that be a lower threshold? Should it be a higher threshold? There are a lot of questions that are coming up, and I think we'll continue to evaluate the research findings that come out in the next few years and potentially take some action on that as necessary. But it could be that something entirely different is needed to account for HSI, and I think we'll figure that out as we go forward. But thank you for the question.
All right, Keith, thanks again for such a great talk.
Yep, thank you, Mike. Appreciate it.
All right, that ends today's seminar. Thanks everyone for joining. Have a great one.